is the final length, L1 is the original length, theta 1 is the initial temperature, and theta 2 is the final temperature. From equation 1, we can make L2 the subject of the formula, which is equal to L1 in bracket 1 plus alpha T, where T is the temperature rise. The unit of linear expansivity is per Kelvin. Area expansivity. Area expansivity beta of the material is defined as an increase in area per unit area per degree temperature rise. Beta equal to increase in area over original area times temperature rise, which is also equal to, in bracket, A2 over A1 minus 1, all in bracket 1 over theta, where A2 is the area after expansion, A1 before expansion. In theta is change in temperature. The unit is per Kelvin. Volume expansivity. Volume expansivity gamma of the liquid is defined as an increase in volume per unit volume per degree rise in temperature. Gamma is equal to increase in area over original volume times temperature rise, which is equal to V2 over V1 minus 1, all in bracket 1 over theta, where V2 is volume after expansion, V1 is the volume before expansion, theta is change in temperature, the unit is per Kelvin. Relationship between area and volume expansivities. If alpha is coefficient of linear expansion of a metal, its area expansivity beta and volume expansivity gamma are related by alpha by beta equal to 2 alpha, gamma equal to 3 alpha. Thus, we can write the following: area after expansion is equal to area before expansion in bracket 1 plus beta, is equal to area before expansion in bracket 1 plus 2 alpha. V2, which is volume after expansion, is equal to volume before expansion in bracket 1 plus gamma, which is also equal to volume before expansion in bracket 1 plus 3 alpha, where A1 and V1 are the original area and volume respectively. V2, A2 are the final area and volume respectively. Change of density of a substance with change in temperature. D is equal to M over V, mass over volume. Therefore, mass M is equal to dV, where D1, D2 are the initial and final densities respectively. V1, V2 are the initial and final volume respectively. Assuming M is constant, D1, V1 equal to D2, V2, which is equal to mass, which is a constant. D1 over V2 equals to D2 over V1, which is equivalent to D1 over D2 equals to V2 over V1. Gamma is equals to V2 over V1 minus 1, all in bracket 1 over theta. Gamma theta plus 1 is equals to V2 over V1. V2 is equal to, in bracket, gamma theta plus 1 times V. From equation 1, you know that V2 is equals to D1 V1 over D2. V1 is equals to, in bracket, gamma theta plus 1 is equals to d1 v1 over d2. Therefore, d2 is equals to d1 v1 all over v1 in bracket gamma theta plus 1. This is equals to d1 all over gamma theta plus 1. Apparent cubic expansivity. The apparent cubic expansivity gamma A of a liquid is defined as the increase in volume per unit temperature rise relative to that of the material of the vessel. Apparent expansivity gamma Y may be expressed as follows: gamma Y equals to mass of liquid expelled over mass of liquid remaining times temperature rise, which is equal to gamma R plus gamma. The absolute or true temperature is equals to apparent expansivity of the liquid plus volume expansivity of the containing vessel. Relative cubic expansivity. Relative cubic expansivity is defined as the increase in volume of the liquid per unit volume per rise in temperature when the liquid is in a vessel. Gamma A is equals to V2 minus V1 all over V1 theta. Experiment measuring of gamma A. Weight of empty beaker equals M1. Weight of beaker before heating plus liquid equals to M2. Weight